second midterm practice exam, problem 8. For a hemispherical dielectric, that's this green hemisphere here, with a locked-in polarization. So I tried to draw that with the red arrows there. I have several things. I need to find the bound volume and surface charge densities. I want to use those to show that the total charge is 0. I want to find the dipole moment, so that should be a lowercase p, dipole moment for this whole thing, and then not calculating, but simply sketch the electric field E for the system. So lots of things to do, so let's get started. First thing that I need to do is write down what the polarization field for this guy is. And so the polarization field, right, it's a vector field, so it depends upon position. But for us, it's actually really easy. It's just some uniform polarization in the k direction in hemisphere, and 0 otherwise. Okay, and so that's going to make things really easy on us. Because for part A, we're asked to find rho. Well, the definition for rho is minus the divergence of this polarization. But if the polarization is constant here and constant here, this is 0 everywhere. Okay, and so we find that this is 0. For the surface current, it's a little bit different, right? For this is n hat dot p. And so we can break this apart. We can look this at the top. So rho on the top, or sigma on the top. N hat in this case, right? Will depend on this polar angle theta. And so it's just going to be P naught times cosine theta, because the dot product depends on the angle between those. So if the polarization is in the k direction, which it is here, then this is just going to be P naught cosine theta. For the bottom, n hat is going to be in the minus k hat direction, and so sigma bottom, the bound charge, is simply minus P naught. And so there we go. Now we have found all of the bound charges for this system, simply applying these equations. For part B, show that the total charge is 0. And so I'm going to write this out as the integral d2x, right, over a closed surface of the bound charge, because the volume is 0, so I'm just going to ignore that. I'm going to break this up into two parts. I'm going to integral d2x over the top of the top plus the integral d2x over the bottom, sigma bottom. The bottom is by far the easier to do, right, because it's constant, and so I just need to multiply by the area of that. If I define the size of this hemisphere as capital R, and this is just pi, so this is going to be minus pi r squared times rho naught, the minus from there. Okay. So now we have to do the top. The top's a little bit trickier. We have to actually perform the integral. And so carrying this around, this is going to be integral of d theta sine theta, integral of d phi. This goes from 0 to pi. This goes from 0 to pi over 2, 0 to 2 pi, 0 to pi over 2. And multiplied by the radius squared. So this is the surface area element in polar coordinates. Then I'm going to multiply this by P naught cosine theta. So this part's easy, so this is going to be 2 pi from this one right here. So this gives me my 2 pi. I'm going to have r squared P naught, and that's the r squared and the P naught. And then I have an integral from 0 to pi over 2, sine theta d theta, cosine theta. Now we do a substitution, right? And the substitution we do is that cosine theta is equal to u. That's going to change this integral into an integral from 0 to 1 du times u, which this one's trivial to do. That's just 1/2, right? Because it's 1 over u squared evaluated at 1 and 0, and so it's just 1/2. Or it's 1/2 u squared evaluated at 1 and 0, so it's just 1/2. And so the 1/2s, of course, this 1/2 will cancel with that 2, of course, and that will give us that the total charge, right, is going to give us a positive pi r squared p naught minus a negative pi r squared p naught, which is, of course, 0. And so we have confirmed that the total charge is 0 for the system. Now we want to find part C. Okay, find the dipole moment. And so here it helps to remember what the definition of the polarization is. So the dipole moment is simply the volume integral of the polarization, right? That's actually pretty easy. The polarization is the dipole moment per unit volume, so the dipole moment is the volume integral of the polarization. For us, this is easy because it's a constant, and so this is just going to be rho naught times whatever this volume is, and so this is going to give that our dipole moment is 2 pi capital R cubed p naught over 3, because it's half the volume of the sphere. So instead of 4/3, it's 2/3. And so that was really easy. And then for part D, we want to sketch the electric field. Okay, so this isn't too bad. So let's go ahead and draw our hemisphere. Okay, so there's our dielectric hemisphere. We know that we have a uniform negative surface charge on the bottom, and we know that we have a positive surface charge on the top half that is more concentrated on the top and less concentrated on the sides. And so the highest density is there in the center. And so taking these and drawing electric fields, we first see that in the interior of this guy, we're going to have an electric field that points from the positive charges to the negative charges in the opposite direction of the polarization. This should be standard for all locked-in polarizations, that the electric field due to that polarization is in the negative direction of that electric field, or of that polarization, in the opposite direction. And then here we should find that we have some behavior like this. And this should make sense because this looks like a dipole field, and that's what we calculated above was the dipole moment. And so again, unless you have multiple parts with multiple different polarizations, or you have a non-uniform polarization, in general your field will look like a dipole field. There you go. Okay, good luck on the exam. Have a good time.